Good afternoon. We are meeting once again. Our topic for today is Otto Cycles, power machines in 6. So Otto Cycle basically is the same thing as a constant volume cycle. If you look at our graph, which we have drawn here, you can see now that on our graph, the process starts at this point marked T1, or our A, point marked A. That's where the compression stroke starts and it ends at point B. Now, the start of point B is the constant volume process which ends at point number C. Now, at the start of point C, that is the beginning of the expansion stroke, which ends at point D, which is our the end of the expansion stroke. Between D and A, we have the heat rejection or the exhaust. One more exciting thing about the Otto cycle or the constant volume cycle, we basically have two volumes. As you can see, we have V1, which is equal to our V4, and we have V2, which is equal to our V3, which is also equal to our clearance volume. Maybe there might be one or two things that you must need to remember when you are dealing with cycles. Now, when you are given a 4-stroke engine, to get our C, which is the number of firing strokes, you divide your speed divided by 2, the speed at which that engine was running. And then C, if it's a 2-stroke engine, equals to the speed. In other words, the number of firing strokes equals to the speed at which that engine is running. And then lastly, C is equal to your speed times 2 if it's a double acting engine. And then I think we are familiar with these formulas for calculating indicated power. We can use plane over 60 or place over 60. We also have our formula for calculating brake power, which we can use a plane over 60 or place over 60, depending on the situation that you are dealing with. Where our B, that's our brake mean effective pressure, our L, the stroke length, A, that's our area, our N, that is the number of firing strokes, and then E, the number of cylinders. Now we have a question which I've taken here. It's from the textbook by Hegner and Detroit. It's activity 3.1, which is question number 6. The question reads, an engine working on a constant volume cycle has 4 cylinders and operates on the 4-stroke Otto principle at 3,000 revolutions per minute. The engine has a compression ratio of 8.6:1 and develops an indicated power of 30 kilowatts with an indicated mean effective pressure which is equal to 700 kilopascal. Compression and expansion index, our N, equals to 1.3. The piston diameter and stroke are equal. The pressure at the start of compression stroke, the pressure at the start of the expansion stroke is said to be 90 kilopascal, and the highest pressure on the cycle, is said to be 4,400 kilopascal. Calculate the piston diameter. So that's the first thing that we are supposed to look at. The question says calculate the piston diameter. So we can use our formula IP equals to a plane all divided by 60. Now let us check here. We are given our IP, which we said our IP is given as 30 kilowatts. Our mean effective pressure, it was given as 700 kilopascal. Our stroke length, there is an emphasis which said a piston diameter and the stroke length are equal. So if they are equal, which simply means therefore, our formula for calculating area, we say area equals to pi d squared over 4. But because our L and our D are said to be equal, therefore it becomes pi d cubed over 4 times our N, which is the number of firing strokes. What's our speed? Is 3,000 revolutions per minute. Which type of engine are we dealing with? We are dealing with a 4-stroke engine. So if it's a 4-stroke engine, like what I mentioned earlier on, a 4-stroke engine, we divide our speed by 2 to get our number of firing strokes. So we divide it by 2 times E, number of cylinders. We are given 4 cylinders, so it's 4. So from there, we can make our D a subject of the formula. Therefore, D equals to cube root of, we have 30 times 4 times 2. Don't forget, everything here has to be also divided by the 6. Don't forget that 6. Don't forget that 6. So everything should be divided by 6 because we want to change our IP to be in seconds. So we divide that by 6. So which also becomes times 6. Divide by, what do we have there? 700 kilopascal times our pi times, what else do we have there? 3,000 times, lastly we have our 4. Perfect. So let's see what are we getting there. Let's see what are we getting. Okay, 30 times 4 times 2 times 60. So it's fine there. So we have 30 times 4 times 2 times 60 divided by 700 times pi times 3,000 times 4. I'm getting 0.0817 meters. But they want the answer, the piston diameter in millimeters. So we simply times it by 1,000. I'm getting something like 81.717 millimeters. So we are done with our A, which is our piston diameter in millimeters. Number B, they want us to calculate the volumes in centimeter cubed at all the cardinal points of the cycle. So we need our V1, which is our V4. We need our V2, which is our V3, or our clearance volume. Now that we have our diameter, it becomes easier. For number B, we can simply say, but swept volume equals to pi d squared over 4 times our L, which becomes pi times our diameter. We got it as 0.0817. Don't forget to square it over 4 times our L. Our L was equal to our D, so times 0.0817. So let's get our swept volume. Perfect, which is I'm getting something like 4.2 283 times 10 raised to the power of negative 4 meter cubed. But they want the volume to be in centimeter cubed. So we are going to say 4.283 times 10 raised to the power of negative 4 times 10 to the power of 6. So we simply multiply by 10 to the power of 6, changing it to centimeter cubed. So it becomes 428.3 centimeter cubed. Now we have our swept volume. The second thing that we need to do now is to get our CV, which is our clearance volume, as well as our V2 and our V3. So CV equals to V2, which is equal to V3. So we are just looking for one volume there. But to get our CV, CV equals to swept volume over our compression ratio. Our SV, we got 428.3 centimeter cubed, divided by, so here it becomes CV equals to swept volume divided by our compression ratio minus 1. So our compression ratio was given as 8.6. So 8.6 minus 1 gives us 7.6. So let's get our CV. So 428.3 divided by 7.6. I'm getting 56.4. 56.4 centimeter cubed. So here we are done. 56.4, that's our CV, and that's our V2, that's our V3. So they want our answer to be in centimeter cubed. So we are done on that part. So what is left is for us to get our V1, but we said earlier on, our V1 is equal to our V4. So V1 is equal to V4. How do we get it? It's SV plus our clearance volume. SV 428.3 plus 56.4. Let's see what are we getting there. 428.3 plus 56.4. I'm getting something like 484.7 centimeter cubed. So we have all the volumes which are needed. We have all our volumes. We have our swept volume. We have our clearance volume, our V2 and our V3, which is 56.4. And then we have our V1. So we are done on point number B. Now let's reflect on point number C. On number C, they want us to calculate the pressures after compression and after expansion. So we need to calculate the pressures after compression as well as after expansion. So we need the pressures after expansion, compression ends here. So we are looking for P2 and the pressure after expansion. This is our expansion stroke. So pressure after expansion, that's our P4. So let's get our P2. So which formula can we use to get our P2? P2 equals to P1 into, we can use the ratio of our volumes, V1 over our V2 to the exponent of n. Now, if you want to use the ratio of the volumes, which is the one that we calculated here, we can use them. But since we are also given our compression ratio. You can also use it. That one is quite easier. It's allowed. It will still give you the same answer. Yeah, so our P1, the pressure at the start of the compression stroke was given to be 90. So let's substitute here. We have 90 into our V1. So we are using the ratios. So on our ratios, V1 is equal to V4. So we said that V1 equals to V4, which is 8.6. But clearance volume equals to V3 equals to V2, which is equal to 1 from the compression ratio that is given. So our V1, it's 8.6. Our V2 there, it's 1. Our N, it was said to be 1.3. So let's see what we're getting as our P2. 90 times 8.6 to the exponent of 1.3. I'm getting 1476. So I'm getting 1476.014 kilopascal. So that becomes our P2. That becomes our P2. Let's go to P4. We need to also look for our P4, which is the pressure after expansion. So to get our P4, we can use a very simple formula. P4 equals to P3 into V3 over our V4. V3 over our V4 to the exponent of our N. Now, do we have our P3? Our P3 is given because the question says, and the highest pressure in the cycle is 4,400. So that's our highest pressure. So the highest pressure on an Otto cycle is 4,400 into our V3. What's our V3 from our compression ratio? It's what? It's 1. And then our V4 from the compression ratio, it's 8.6 to the exponent of 1.3. So let's see what are we getting there. 4,400 times 1 over 8.6 to the exponent of 1.3. I'm getting 268.3 kilopascal. So now we have all our pressures on the cycle. So the most important thing when you get your pressures, you need to look to interpret your graph properly. We say the highest pressure on the cycle should be P3. So it's given as 4,400, followed by P4. What's the size of our, followed by our P2. Yes, our P2 has to be higher pressure, as well as our P3 and our P4. You just compare the values. They need to be on the right track there. Now we have all our pressures. Where do we need to go to? We need to go to our number D. For number D, what are they saying? We must look for the work done per cycle. So we need to calculate our work done per cycle. Which formulas can we use? We have a number of formulas which we can use. We can use IP, work done equals to IP over our N divided by our E. So this is a simple formula for work done. It has to work. If we had to use that one, our IP was given as what? Our IP was given as 30 kilowatts. So you can say 30 times 10 raised to the power of 3. We are simply changing our kilowatts to watts. So divide by our N. What was our speed? Our speed was 3,000 revolutions per minute. So we must not forget that the engine that we are dealing with, it was a 4-stroke engine. Therefore, we need to reduce our speed to the number of what? Firing strokes. So we need to divide it by 2. Or in other words, we could have just substituted 1,500 here, but whatever way is still going to be the same thing. And then you divide it then by our E, where E, the number of cylinders, which is what? 4. Let's see what are we getting there. So we have 30 times 10 raised to the power of 3 divided by 1.5 divided by 4. And see what are we getting there. 30 times 10 raised to the power of 3 divided by 'So I'm getting something like 300 joules per cycle. And then the second formula which we could have used to calculate our work done, we could have said work done equals to P3 V3 over N minus 1 minus P4 V4 all over N minus 1 minus P2 V2 minus P1 V1 all over N minus 1. So if we were to use that one, it has to work, but I think this is a thing that we can do. Let us try to use that formula to see what are we getting. Work done equals to P3 V3 minus P4 V4 over N minus 1 minus P2 V2 minus P1 V1 over N minus 1. So we have all our, P3, we have our V3, and then we have everything at our disposal. Now, just because of space, let me just try to put the values. Our P3, we have P3, which is 4,400 times our V3. Our V3, the easier thing which you can do, you can use from the compression ratio. But if you want to use the one that we calculated, is still fine. But I will stick to the ones that from the compression ratio. Our V3 from compression ratio, it's 1. Let me just write it so that everyone can see. So it's 4,400 times 1 minus P4. Our P4 we said is 268.3, and it's 1.3 minus 1 times, minus times V4 is what? Our V4 is 8.6. Perfect. Minus P2, our P2, we got our P2 is 1476.014. V2, our V2, we said it's 1 times 1 minus P1, it was given as 90, and then our V1, it's 8.6. all divided by n minus, rather not n, is now 1.3 minus 1. So let's see what are we getting there. $4,400 times 1 minus 268.3 times 8.6 divided by 1.3 minus 1. Okay. Minus 1476.014 times 1 minus 90 times 8.6 divided by 1.3 minus 1. Let us see what are we getting. I'm getting my answer is 261. 261.66 joules per cycle. So these are the two answers which we can get on this part. These are the two answers which you can get on this part. They are different values, but they are both acceptable. Perfect. Now let's go to the last part, which is our point E. On point E, they want us to calculate all the temperatures at the main points of the cycle if at the start of the cycle on the compression part our temperature is said to be 350, which is our T1. So let's look for our T2, our T3, as well as our T4, because the other ones are given. So to get our P2, we can use our formula P1 V1 over our T1 equals to P2 V2 over our T2. So we have everything at our disposal with the exception of T2. So we make T2 subject of the formula T2 equals to T1 times P2 times V2 over P1 times V1. So we can use our T1 is said to be 350 kilopascal. Our P2, we said P2 is 1476 times V2. We can stick with those ones which we got from our compression ratio. So our V2 from the compression ratio, we got it as what? Our V2. Our V2 from the compression ratio. What's our V2? Our V2 is 1. So whether we substitute it, it won't make any difference. Our P1 is 90 kilopascal, which is the pressure at the start of compression. And then our V1 is 8.6. So let's see what are we getting there. 350 times 1476 divided by 90 times 8.6. I'm getting 667.442 Kelvin. That's our T2. So now let's go to our T3. Let's go to our T3, but P2 V2 over T2 equals to P3 V3 over our T3. So, but there's one thing that you must remember. This is an Otto cycle, and we made it clear that V3 and the V2 are the same. So if V2 is equal to V3, what are we saying here? We take this out, we take this out. So from there, we make our T3 subject of the formula. So T3 equals to T2 times P3 over P2. So let's see what are we getting. Do we have our T2? Yes, we got our T2 as 667. So we have 667.442 times our P3. P3, that is the pressure. There is pressure on the cycle, which is 4,400 all over P2. Our P2, we looked for it, we got it as 1476 divided by 1476. So let's see what are we getting there. 667.442 times 4,400 divided by 1476. I'm getting 1989.665 Kelvin. So that becomes our T3. And lastly, let's wrap up with our T4. So T4, we use our formula P3 V3 over T3 equals to P4 V4 over our T4. So let's look for our T4. Therefore, T4 equals to T3 times P4 times V4 over P3 times V3. Our T3, we said it's 1989.665 times our P4. Our P4 we got as 268.3. 268.3 times our V4. Our V4 is same thing as V1, which is our 8.6 divided by our P3. Our P3, which we said is our P3, that is the highest pressure on the cycle, which is 4,400 times V3. Our V3 from here, it gives us, it's 1. So let's get our answer. 1989.665 times 268.3 times 8.6 divided by 4,400. So I'm getting 43.389 Kelvin. Yeah, 43.389 Kelvin. So that becomes our final answer. So the most important thing here is not about just getting the answer, it is understanding the type of cycle that you are dealing with. And you must also remember your formulas and the number of firing strokes per different engines that you might be given or that you might be dealing with. Yeah. So let's meet on the second part as I will be attending to a question for a diesel cycle. Thank you.